The event will begin in 5 minutes.
سيبدأ الحدث في غضون 5 دقائق.
Que una hembra gitana conjuró a la luna hasta el amanecer. Llorando pedía al llegar el día de esposar un calé. Tendrás a tu hombre piel morena, desde el cielo habló la luna llena. Pero a cambio quiero el hijo primero que le engendres a él. Que quien su hijo inmola para no estar sola, poco le iba a querer. Luna quiere ser madre y no encuentras querer que te haga mujer. Dime, luna de plata, ¿qué pretendes hacer con un niño de piel? Hijo de la luna. De padre canela nació un niño, blanco como el lomo de un armiño, con los ojos grises en vez de aceituna, niño albino de luna. Maldita su estampa, este hijo es de un payo y yo no me lo callo. Luna quiere ser madre y no encuentras querer que te haga mujer. Dime, luna de plata, ¿qué pretendes hacer con un niño de piel? Hijo de la luna. Gitano al creerse deshonrado se fue a su mujer, cuchillo en mano. ¿De quién es el hijo? Me hace engaño fijo y de muerte la hirió. Luego se hizo al monte con el niño en brazos y allí le abandonó. Luna quiere ser madre y no encuentras querer que te haga mujer. Dime, luna de plata, ¿qué pretendes hacer con un niño de piel? Hijo de la luna. Y las noches que haya luna llena será porque el niño esté de buenas. Y si el niño llora, menguará la luna para hacerle una cuna. Y si el niño llora, menguará la luna para hacerle una cuna.
Please be seated. The event is about to begin.
يرجى منكم التكرم بالجلوس. سيبدأ الحدث بعد قليل.
Ladies and gentlemen, please put your phones on silent.
سيداتي سادتي، يرجى وضع الهاتف المحمول على وضع الصامت.
Good afternoon, ladies and gentlemen. Welcome to day 3 of WEP 2026 and today's keynote session titled The 2027 Solar Eclipse over the Kingdom of Saudi Arabia. Hopefully something you all get to witness. Once again, before we begin, I would like to remind the students taking WEP for credit to please check in before the session and do not forget to check out specifically after the Q&A has concluded. This afternoon, we're pleased to have Dr. Thibault Larry, Director of Strategic Insights in the Office of the President here at KAUST, who has the honor of introducing our keynote speaker and to moderate the Q&A session. A bit about Dr. Thibault. He has a PhD in computational astrophysics and experience spanning academia, European research policy, and strategic leadership. He has contributed to establishing the European Research Council and worked with the European Space Agency. Ladies and gentlemen, please join me in welcoming Dr. Thibault Larry to the podium.
So, welcome everyone to talk to us about the 2027 eclipse visible here in Saudi Arabia. I'd like to introduce Dr. Alexandra Lockwood. She's currently the Director of Strategic Development at Computational, Inc. in the US. But honestly, I think she has the coolest CV in the room. And here are 4 reasons. I'll give you why. Number 1, she holds a PhD in planetary sciences from Caltech. So planets, exoplanets, star systems have no secrets left from her. Number 2, she worked at NASA, at the James Webb Space Telescope. I'm sure you've heard about this telescope. So when you see those mind-blowing space photos on Instagram or TikTok, there is a good chance she was involved behind the scenes. Third, she's a genuine movie star, not kidding. If you've seen the movie, the PhD movie number 1 or 2, you know exactly who I'm talking about. If not, go and watch the 2 movies. You are looking at the main character. Number 4, here is the part that matters the most to us. Before all of that, she has spent 2 years right here at KAUST, where she launched the KAUST Discovery magazine and the Sci-Cafe programs. So she's not just a guest, she's one of us. So she knows our campus, she knows the star, she is a star. So she's here to tell us why the sun is going to disappear in 2027. So please welcome Dr. Alex Lockwood.
Thank you, Thibault. Thank you so much. What an introduction. Whew. Hello. It's wonderful to be back here at KAUST. My name is Alex Lockwood, and it is truly my pleasure to be able to tell you about an amazing event that will be happening here in a little over 18 months. There's still folks coming in, but we're going to move on with the talk in the interest of time. So there's 4 sections of this talk. We're going to start with what is an eclipse? How does it happen? What are you going to be experiencing? Then we're going to go into some details of what will actually happen on August 2nd, 2027 here in the kingdom and how special it is. We'll talk about the scientific opportunities that are afforded by this eclipse and why we should take advantage of them and make sure that the kingdom is prepared. And KAUST is uniquely positioned to do that. Ooh. And then we'll talk about other ways that we have to prepare the kingdom and KAUST to make sure that we are safe and that we are doing all the science that we can during these few precious minutes of this amazing phenomenon. So you can follow along here on the bottom as we go through the 4 sections in case you need to get caught up, and we'll jump in. So what is an eclipse? The dictionary says it is a total or partial obscuring of one heavenly body by another. This happens throughout the solar system and the universe, but here on Earth, we are especially privy to the sun and the moon interacting with each other. This causes a few different types of eclipses that some of you may have witnessed. In fact, I heard that last May, maybe there was a lunar eclipse here in the kingdom, which is an incredible phenomenon. Total lunar eclipse is something that we can witness here on Earth, as well as an annular solar eclipse and a total solar eclipse. We'll talk about these different geometries in just a moment. However, these aren't the only kinds of eclipses that we have in our solar system. In fact, there's a really amazing picture by the Perseverance rover on Mars that took this image here on the bottom right of one of its moons, Phobos, eclipsing the sun. So as you can see, the size of Phobos is too small to completely cover the sun, so we call it a partial eclipse, but still, other bodies will eclipse the sun as well, and actually this same technique, by covering the sun, can be used in a lot of different ways in astrophysics, which I'll mention later. So, this is the geometry for a total solar eclipse. On the left, you see the sun, and in between the sun and the Earth is the moon. The light from the sun passes by the moon, and the moon's shadow on the Earth is called the eclipse. Where the moon completely blocks the path of the sun is called a total solar eclipse, and it is a very small part on the Earth. Here it's labeled as the umbra. That's where you're going to get a total solar eclipse. A total lunar eclipse is the opposite geometry, where the moon is on the other side of the Earth from the sun, and it's actually the Earth's shadow that's covering the moon. However, light from the sun refracts around the Earth's atmosphere, still hits the moon, so the moon is still visible to us, but because the light's refracted through the Earth's atmosphere, the blue light is more easily scattered away. The red light continues on to the moon, and that's why you get a red-looking moon during a lunar eclipse. So, same three bodies, different geometry, different types of eclipses. However, we know that the moon goes around the Earth approximately once a month, every 28 and change days. So why don't we have an eclipse every single month? That would be lovely. It's a very beautiful sight. But you actually have a tilt to the moon's orbit that means that only once every approximately 18 months does the moon actually land either between the sun and the Earth or on the other side of the Earth in the Earth's shadow. So the orbital tilt of the moon is one of the reasons that we don't have an eclipse every single month. That's the biggest reason. The other reason is that the orbit of the moon is not entirely circular. It's elliptical, and so there are times when the moon is closer or further from the Earth, and if it's further from the Earth, closer to the sun, you're actually going to get what we call an annular solar eclipse. These happen also approximately once every 18 months, and they are spectacular to witness, but they are not quite as special or as awe-enveloping as a total solar eclipse, which is happening here in just over 18 months. So you have these different geometries between these three bodies, and they actually afford us the fact to witness a total solar eclipse. I just want to emphasize how incredibly special this is, because if we look at this again and we actually look at the geometry, this is not to scale. We zoom out and we look at the actual sizes and distances between these things, and the fact that it ever lines up is amazing. The fact that you have a body that is 400 times smaller, the moon is 400 times smaller in actual size than the sun, and yet the apparent size of the moon exactly matches the apparent size of the sun, that's incredibly rare. And it's not going to happen forever. Currently, the moon is moving away from us, stealing angular momentum from the rotation of the Earth, and eventually the moon's going to move far enough away that we will never have a total solar eclipse. But it's not going to happen in our lifetimes, and more importantly, you will get to witness a total solar eclipse here at KAUST next summer. So let's talk some more about that. I want to emphasize how rare it is and talk a little bit about some of the past eclipses that we've had. and what we've learned from them so that we can talk about what we're going to learn from this one. This is a map, a heat map of 5,000 years of eclipses. So this is all of the eclipse paths for 5,000 years plotted on the Earth. As you can see, the scale only goes up to about 35. So if you're the luckiest person in the Arctic, living in the Arctic, maybe you will get 35 eclipses in 5,000 years. That's on average, any place on Earth gets an eclipse once every 375 years. Very, very rare. Over the last decade, and I mean 2010 to 2019, there were 7 eclipses. They're shown here. What I want you to notice here is that most of the eclipses are not over land. If you think about it, it makes sense because most of the surface of the Earth is covered in water. But it also means that being able to be on land where we live to witness an eclipse is that much more rare. I've also highlighted the eclipse from 2017, which went over the continental US, from which I'm going to share a lot of the science that's been studied. There's also a lot of science that's been done on the 2019 and 2020 eclipses over South America. And then if we move into the 2020s, more recently, the US had an eclipse in 2024 that I was a major part of, and part of the reason that I'm giving this talk is to share with you what I've learned from that. But a lot of the science hasn't been published yet from that eclipse. So again, most of the eclipse paths are over water. It's actually rare for it to, hit a large portion of land. And it's hard to tell here because of the Mercator projection of the map, but the width of the path, the eclipse path, actually corresponds to the length that you're going to experience the eclipse. And because of the Mercator projection, number 6, our 2027 eclipse doesn't look as wide as it should, but this eclipse that's going to happen in 2027 is the longest eclipse of the 21st century. And I can tell you, having experienced an eclipse that was about 1.5 minutes in 2017 and an eclipse that was 4 minutes in 2024, the more time that you can spend in totality, the more you get to experience, and we'll talk about that. And also the more science you can do. So this is an incredibly special, rare opportunity for the kingdom to do science. And I want to make sure that we are prepared. And I do say we because KAUST is still a part of me. As I mentioned, I worked on the 2024 solar eclipse. I was part of NASA for 3 years. And for 2 of those years, I was preparing for the April 8th, 2024 total solar eclipse. Fun fact, it's also my daughter's birthday, so it was a very special day. But I was responsible for organizing all of the sites across the US that were going to host in-person people to witness the eclipse. We had 13 sites along the path of the eclipse and over 300,000 people who came to those sites to witness the eclipse. We also had over 40 million people watch a live broadcast over 3 hours. And NASA distributed over 2 million glasses to different people. Now, we had a lot more than 2 million people who were watching this eclipse across the US, but that's what NASA was able to contribute for free to make sure that people were safe. And we'll talk more about eclipse glasses, but they are very important. We also had an annular eclipse that I was part of, which again was a very exciting and actually much more, inspirational event than I thought it was going to be. I kind of thought it was boring compared to the total solar eclipse, but it was also really special. And if you ever get a chance to witness that, I would encourage you to do so. But I spent 2 years of my life preparing for this eclipse in 2024. There's a lot of work to be done to make sure groups are ready, a place is ready to handle what's to come. And so I bring that experience here to this talk to make sure that KAUST and the kingdom are ready. So on August 2nd, 2027, the moon's shadow is going to pass over the Earth, as you see here. It passes through North Africa, it passes down through Saudi Arabia and out Yemen into the ocean. I'm going to play that again, just because it's an interesting animation, and you may want to see again. Let's play it again. There we go. As you can see, it passes over Morocco, southern Spain, a large portion over Egypt, through Saudi Arabia and Yemen. Jeddah is the largest city that the eclipse passes over. Other large cities include Luxor in Egypt and Tangier in Morocco. But these already, people are already looking to travel to those places. And we'll talk about the tourism that comes with an eclipse. Here is a picture of the entire map. As you can see it, Spain, Algeria, Morocco, Saudi Arabia. And if we zoom in on Saudi Arabia, you can see that not only does it pass through Jeddah, but it passes through other major cities, including Mecca, Abha, Sana'a, Taif, and KAUST. And in fact, that's KAUST plotted on the map right there. I'm going to zoom in a little, I'm going to zoom out. If you go to the KAUST beacon, which I feel like would be a very incredible spot to witness a total solar eclipse, you will get 4 minutes of totality. If you go south, and just south of Jeddah, where this dotted line you can see in the middle, that is the maximum totality. Any area in this dark red region, you're going to receive a total solar eclipse where the moon fully covers the sun. Outside of that, where it's less shaded, you'll get a partial solar eclipse, which are still interesting. But anywhere within this dark red region, Taif, Mecca, Abha, Jeddah, KAUST, you will get a total solar eclipse. The closer you go to that dotted red line, the longer a total solar eclipse you will get. So if you go about 40 kilometers south of Jeddah, right to where that dotted red line hits land, you can get all 6 minutes and 24 seconds of totality. Now, this may not seem like, why would I go to the south of Jeddah? I can just witness here from KAUST. Amazing, stay at KAUST, that's great. However, for science purposes, we need to make sure that we are having scientific instrumentation along that dotted line. Why? Because the science that can be done during an eclipse is incredibly valuable and incredibly rare. This is the longest eclipse in a century. I just showed you over the past 2 decades, there's only been 14 eclipses. This means that in 20 years, you get less than an hour worth of science. So when you're talking about an hour of opportunity in 20 years, you want to get every second of that opportunity. So let's talk about what that opportunity is for science. There are kind of 2 different kinds of science. I break it into 3 different kinds of science that you can do during an eclipse. 1, to study the sun, and especially the atmosphere of the sun called the corona. The other thing that you can do during an eclipse is study our atmosphere between here and the sun and how it responds to the changes of turning off the sun for a few minutes. That doesn't happen. It happens once every 18 months, and the atmosphere is used to a diurnal cycle of day and night that happens over hours. Eclipses have happened since the beginning of humanity, and they've been documented in pictograms for hundreds of years, but the first science started really in the 1800s, where folks learned that, hey, something's happening, what can I learn from it? These are some pictures, hand-drawn pictures taken of folks looking at eclipses in the 1860s, and discoveries were made from these of coronal mass ejections, which are a really important solar phenomenon. That's, you can see here on the left, that kind of swirly pattern. That was someone trying to draw a coronal mass ejection by hand, which is pretty amazing because this is the only time that you can see a coronal mass ejection with your eyes. And these are responsible for space weather, which affects our telecommunication systems. It affects our GPS. It can take out the power. Space weather is a really important phenomenon, and most of it comes from this outer atmosphere of the sun, called the corona. The other discoveries that were made in the early 1800s include the discovery of helium. We had never discovered helium on Earth because it's a difficult molecule to capture, to analyze. And so the first spectra taken of the solar corona was where we discovered helium. They also discovered something they called coronium after the corona. Turns out it was just very highly ionized iron, but it was very highly ionized. It was a completely new ionization state that they'd only witnessed in the corona. when this happened, when they knew the eclipse was coming, they were actually looking for new planets in the eclipse, because when you block out the light from the sun, you can see things that are much closer to the sun. And they theorized, because of weirdness in Mercury's orbit, they theorized that there was planets inside Mercury's orbit. Spoiler alert, there's not planets inside Mercury's orbit, but we actually still use the same technique of blocking out starlight to look for planets around them. It's called direct imaging, and it is one of the main techniques that's used to both discover and characterize extrasolar planets. So, we've used eclipses for many, many years to do all sorts of heliophysics, astrophysics, and other types of physics. So in 1919, Sir Eddington took a voyage to study the solar eclipse in order to confirm Einstein's theory of general relativity. Einstein's theory of general relativity, as I'm sure you know, says that a massive object will warp space-time, and one way to test this is to see light bending around a massive object. The closest massive object is our sun, but you can't see anything near our sun. It's too blinding. So what they did was they took images of the night sky that they anticipated during the eclipse, and then they waited for the eclipse to happen and took images of the same stars and looked to see if they moved. Because, as you can see here in this beautifully captioned in German image that I found, the light bends around the sun, and so the apparent projection to our eyes is somewhere different than the actual position. This photo on the right is an actual photographic plate taken by Eddington of images of the stars at night and images of the stars during the day, during the eclipse. And indeed, you see the motion of the stars due to the bending of light around the sun. So another really important discovery that came out of total solar eclipses was confirming relativity. Now we'll talk about some of the science directly related to the eclipses, more modern day. This is a diagram of the sun. Inside you have a very dynamic hot core. The surface of the sun, what we would see when we look at the sun, is called the photosphere. Out of that you have the chromosphere, and then the solar corona. As you can see here, all of your dynamics that are happening on the surface of the sun end up evolving into the corona. Solar flares, coronal mass ejections, prominences, streamers, all of that comes through the corona. And the other really interesting thing is that, as expected from a hot ball of gas that's being held together by gravity, your density falls off as you go away from the surface of the sun. But what's really not expected is that, as you can see here on the right, once you hit about 2,000 kilometers away from the surface of the sun and you enter the corona, the temperature spikes dramatically. Again, this is the only place that you can create in highly ionized iron because it is so hot, millions of degrees Kelvin. And this is one of the biggest questions in the study of the sun, is why is the corona so hot? And this is something that we can study using total solar eclipses, because only total solar eclipses can actually image all of the corona. We're fortunate that we have lots of spacecraft out in space that can study the sun. Lots and lots. We have stereo imaging, we have solar observatories over many years. In fact, this is a picture on the right of the SOHO mission, NASA's SOHO mission, looking at the sun. But you can see that there's a giant circle in the middle where they block out the light from the sun so they can see what's around it. Now, this is the best capabilities that NASA has, and still, that circle is much larger than the size of the surface of the sun, where an image of the surface of the sun is actually inside there. So there's a whole region that missions from space cannot image. The inner corona is only visible and therefore measurable during a total solar eclipse. So what have we learned from studying the inner corona and other parts of the corona? We have discovered argon, we have discovered iron, we've discovered calcium, we've discovered nitrogen, and lots of weaker emission lines that also tell you about the ionization and the dynamic state of the sun's atmosphere, of the corona. More importantly, you can take these spectral measurements, figure out Doppler shifts and line widths, and start learning about the solar wind and all of this energetic activity that is coming off of the surface of the sun through the atmosphere, and much of it is hitting our Earth and affecting our communication system, our systems. So that's a short, brief talk about solar science. I could talk for 4 more hours about it. I'm not an expert, but there is so much work that has been done using eclipses, but also not that much because we've only had very short periods of time to take advantage of this. So again, this work is from the 2017 eclipse. There's been work done on the 2019 and 2020, but this is, the kingdom faces 6 minutes of the ability to do groundbreaking science, and I'm really excited for what is going to come, the science that's going to come out of this next eclipse. So in the interest of time, we're going to go to the next area of study, atmospheric science. We study the atmosphere every day with tons of different satellites, ground-based measurements. We can make global maps of the atmosphere, temperature, pressure, composition, what is it made of? How is that nuanced? The winds, zonal, meridional, electromagnetic fields. We have tons of maps of these. However, the eclipse is a very unique time. It's kind of a laboratory experiment when you get to turn off a single external stimulus and then turn it back on and see how the atmosphere responds. There's a spatial response, there's a temporal response. You never get this in atmospheric science. So atmospheric scientists, I'm looking at you. I can't see any that I know in the audience, but this is an incredibly unique time to study the dynamics of the atmosphere, which are incredibly complex because in addition to having a 2D, spatial coverage over the Earth, you have a 3D system, many, many layers of the Earth, for those of you who are familiar with atmospheric physics. We live here in the troposphere, then you have the stratosphere, the mesosphere, and the thermosphere, and then the exosphere is when you get really, really low density, really entering into space there. But you have different layers of the atmosphere, and for those of you who have studied atmospheric physics or science, you know that temperature, pressure, all sorts of chemistry changes at each of these different layers. So once again, we're looking at the same different measurable measurements. We're looking to understand temperature, winds, composition. And if we look at the lower atmosphere, it's really easy to study the lower atmosphere. We can take in situ measurements. There are thousands of weather stations across the globe measuring temperature, measuring winds, measuring pressure. Additionally, we can get up pretty high in the atmosphere with things like weather balloons, sounding rockets. You can put a payload on a sounding rocket, you can send it up, and you can take measurements for dozens of kilometers up into the atmosphere. You can get well into the stratosphere. However, it's much harder to study the upper atmosphere, which is why we kind of break them out. So I'm going to spend one slide talking about the science of what we've learned from the lower atmosphere. Here you see results from 3 different studies, 2 different eclipses. On the right is the 2024 eclipse. There has been some scientific data published. And I'm showing here 2 very different sets of data. The one in the middle was taken by a researcher, a scientific team, scientific instrumentation, very well calibrated, very precise. And the one on the right is actually taken by a group of students who made their own instruments in their lab. These are undergraduate students, made their own instruments in their lab and put out some payloads and sent up a couple of weather balloons. So you can see the data on the right is a lot more messy. It's a lot more noisy. But they come to the same conclusions. Both teams see a drop in temperature during the eclipse. Both teams see a drop in winds. So the winds usually die down during an eclipse because the cooling stabilizes the atmospheric boundary layer closest to the Earth. So you get a decrease in temperature, a decrease in winds, and an increase in relative humidity. And I'm just showing you this as an example of what can be done by students to really contribute to scientific understanding. On the left is results from the 2019 eclipse over South America. And it's a terrible graph. I apologize. There was no better graphs that I could grab. But what's actually being showed here is the first evidence of gravity waves that have been induced by the eclipse. Now, I am not an atmospheric scientist. I am a planetary scientist. But I understand that gravity waves, which are waves vertically in the atmosphere that are induced by temperature changes that then change the buoyancy and then are modulated by gravity. So you have these vertical waves that are happening in the atmosphere. They can happen on many different scales, and because they are so 3D in nature and they have different causes, they are one of the highly studied aspects of atmospheric physics. And so here you are actually finding that eclipses do induce gravity waves, which if you think about it, turning off the temperature briefly would do that. But this is the first evidence of that. So what have we discovered? Temperature drops, winds drop, relative humidity increases, and you can induce gravity waves from eclipses. Now we're going to go to the upper atmosphere, and I'm sorry, there's so much to cover, we're going quickly, but I'm going to spend a little bit more time on the upper atmosphere because this is what I've learned. My company, Computational Physics, Inc., specializes in upper atmospheric physics and instrumentation, and so I've been able to learn more about this and can talk about it a little bit more. Plus, it's a really interesting area compared to the lower atmosphere because in addition to the thermosphere and sort of the upper part of the mesosphere, you also have something called the ionosphere, which is completely co-located with the thermosphere and the mesosphere, but this refers to the ionized part of that physical area. So you have the thermosphere, mesosphere, which is the neutral part, and the ionosphere, which is the ionized part. And if you think about it, this is the upper atmosphere, most exposed to solar radiation. You have charged particles that are interacting with the Earth's magnetic field. You have photoionization and photochemistry that is, going on a lot. And so, again, in atmospheric physics, study of what we call but it's also really hard to reach this region of the atmosphere because you're not on the ground and our balloons and rockets don't go up that high. So you can't take any in situ measurements. You can only measure this from remote sensing, either from the ground up or from satellites down. There are a few ways to make in situ measurements using some low Earth orbit or geostationary satellites that go through this region, and you can measure the change in the trajectory as it's influenced by this part of the atmosphere, but those are still not in situ measurements. It's just an indirect measurement. So it's a really, really dynamic area that's hard to study. When I say really dynamic, I mean really dynamic. This is the simplest graph I could find on the internet to explain what all happens in this area. But we want to measure the composition, the temperature, and the winds, but also what is happening with the photochemistry, what is happening with the magnetic fields. And again, to study this really dynamic, interesting system in a laboratory setting where you can turn off one external factor, you can turn off the radiation and then turn it back on, means you get to understand what is happening with the system, how does this radiation, how does the photochemistry really differ from other chemistry or processes that are happening and dynamic processes that are happening in this area. So using the total solar eclipse, this is images from the NASA's GOLD satellite, which measures emission from atomic oxygen and molecular nitrogen, the Lyman-Burge-Hopfield lines. You can measure the emission to basically, not only tell what the emission is, but the relative ratio between these two emission lines, basically we use as a proxy for atmospheric composition. And so you can see that this emission, which is basically mostly caused by photoionization, heavily decreases during an eclipse. So this is differential data. So this was data from the eclipse differenced with data from 2 days before. And you can see a huge drop in emission brightness. So a lot less ionization happening for both of these emission lines during the eclipse. But what's more interesting, and we would expect that, right? You turn off the sun, you turn off the source of photoionization, you get less ionization. Okay. But what's more interesting, and is still a question to be answered, is the fact that when you compare the oxygen and the nitrogen lines, you actually get an increase in that ratio that is up to 80%. It's a very big difference in the ratio of those two abundances. And all I can say is that there's a difference. They have not explained why yet. This is still work in progress, even though it's all the way from 2019. So, there's really the biggest takeaway here is that there's a lot more work to be done, but that we can measure composition from above, but also from below. The other thing that we have measured with NASA's Gold satellite is temperature. We've measured the decrease in temperature as would be expected from a total solar eclipse, but the temperature difference that we've measured is actually about 3 times larger than what the models tell us we should expect. So here you have 100 Kelvin degrees temperature difference that was measured for this eclipse, and the models predicted about 30 Kelvin. One of the things that we use data for is to inform our models, and clearly there's a lot of physics and chemistry in the models that needs to be improved, and we will do that using our data. This is another demonstration of measurement of temperature and winds using a Fabry Pro interferometer on the ground. This is actually really interesting. This was a study that was done using measurements in Brazil, but of the eclipse of North America. So looking at very large global scales of change. And again, they had a model, which is shown here on the left in blue. They had a model, and then the control is in blue. They had the model here is in orange on the left, but then they compare that to the data, and then on the right you can see temperature on the bottom and winds on the top, and the model gets approximately models the data, but it's not enough, and especially you see in temperature, the model does not accurately predict the temperature decrease, and so there are other dynamics that are happening that we don't understand, that our models don't predict, and the best that we can do is try to improve our models using this data. Something is wrong with the physics as it is modeled. Another unique thing about upper atmospheric physics is studying the ionization states. The way that we do this is by taking a measure of the total electron content, TEC, between here and the satellites that are measuring it. This is from 2017 Eclipse. Again, on the left is a model. In the middle is a typical control day. That was data taken about a week later. And on the right, you see a huge decrease in the ionization in the total electron content due to the turning off of the sun. These are all, kind of what we would have anticipated, but having the measurements, having the spatial and temporal understanding of how the atmosphere responds is going to help us, give us a lot of insight into what the composition and dynamics of the upper atmosphere are. Speaking of dynamics, one of the big questions in upper atmospheric science is, what are traveling ionospheric disturbances? How do we predict them? When are they going to come? What are their scales? And I'm going to start going a little faster in the interest of time, but basically we've had 3 different studies that have all confirmed that eclipses can create these traveling ionospheric disturbances. These are really important because the main way that we do communication is by bouncing signals off of the upper atmosphere, the ionosphere. We actually use that for communication signals. And when the ionosphere changes because of one of these events, you can't communicate anymore. And so this is one of the reasons that sometimes the radio doesn't work at night, the AM radio, because anyways. So really the takeaway is there's so many outstanding questions left, and in really important areas like understanding gravity waves, understanding traveling ionospheric disturbances. And the eclipse is just an incredibly unique opportunity to get data that you can't get any other time, because there's no other time where you have such an impulsive event that is affecting the atmosphere. All right, now we're gonna talk about the final section, how do we prepare? This is really important. As I said, I spent 2 years at NASA headquarters working to prepare the country for the eclipse that we had in '24. There was actually another team of folks from the American Astronomical Society who had formed a task force in 2017, after the eclipse in 2017, and worked together as a team for 7 years to try to prepare folks. So I was only at NASA for 2 years doing that. There were folks working for 7 years to make sure that the US was prepared in 2024. What does that look like? Number one most important thing is safety, and a big component of that for eclipses is eye safety. You can't look at the sun. I hope we all know that by this point in our lives. However, when the moon starts passing in front of the sun, it's really beautiful, and you want to look at it. But you need special eclipse glasses to do that. There's a standard from the International Organization for Standardization, ISO 12312-2. That standard says that a solar filter needs to let in less than 1/2 of 1,000% of sunlight. And if your glasses don't say that they are ISO 12312-2 certified, you could damage your eyes, temporary or permanently. Overexposure of the retina it's called solar retinopathy. It has been documented, and it's been documented since the eclipses as well, as because people were not using the right glasses. NASA bought 2 million of these glasses to distribute to make sure that folks could stay safe. I am hoping that KAUST especially, but the kingdom in general, buys these today and gets a lot of pairs of these glasses to keep people safe. One of the problems is the closer you get to the eclipse, you start getting all these fakes pop up. You can buy eclipse glasses for $2 on Amazon. They're fake, they're gonna hurt your eyes, and they can cause permanent damage. There's a lot of news stories that were happening around this. So, if you don't have eclipse glasses, we need to get them, and I'm talking to KAUST in general here, not anyone in specific. You can get a discount if you buy them in bulk. Fortunately, the AAS, the American Astronomical Society that I mentioned, has a website here where they have listed all of the verified vendors of safe solar viewing glasses. So you don't have to figure it out on your own. People have already validated companies who sell good glasses. If we can't get enough glasses, or if folks want to have more of a communal experience, you can make something called a pinhole projector. It's essentially just poking a hole in a piece of paper and then shining it on the ground. And as the sunlight filters through the paper, you actually get a projected image of the sun on the ground. Some folks prefer to do it in a box. There's, again, online you can find activities to make your own pinhole projector using a cereal box. And that just kind of gives you a darker area to be able to see it. But you can see, again, the entire shadow of the moon passing over the sun. When the moon fully covers the sun, you can safely look at the total solar eclipse, which is wonderful. You'll have 6 minutes to stand there, look at the sun, look around you, feel, listen, look at your neighbors, experience your body, look at the sun again, and then put back on your glasses or look through your pinhole projector when the moon starts passing away from the sun. Now, this is something you may not think about, but is really especially important during an eclipse of all phenomenon, a total solar eclipse of all phenomenon. Studies have been done surveying people who have viewed total solar eclipses, and the number one thing that they said that they felt was awe, which is amazing. I have definitely felt awe. I've witnessed 2 solar eclipses. I've definitely felt awe and wonder and inspiration. Euphoria is, some people take it to that level. Another thing people say they witness is connection. People say they were less self-focused and more feeling the community, the connection to others. It is a beautiful thing to witness, very beautiful. However, there are also feelings of anxiety or fear. Folks have anxiety ahead of time. What's going to happen? What are they going to experience? Are they going to get there in time? But also, there's a very primal fear that happens, that descends upon you when the sun goes away in the middle of the day. It gets dark. It gets cold. You feel a chill. The birds stop chirping because they're like, what? The wind dies down, and so the trees stop moving. Everything goes quiet. It is really kind of freaky. And if folks aren't prepared for that, if they don't know that that's coming, and all of a sudden the sky goes dark and they feel a chill, we need to make sure people are aware not only of what's going to happen, but of how they might feel. And there's going to be a lot of people. Eclipse tourism is $1 billion industry. The eclipse that's happening in 2027, it goes over Spain, Morocco, Egypt. There are already 2-week tours that are sold out for 2027 in Egypt and in Morocco for this event. They're even offering tours in southern Spain. They only get a minute of totality. Here in Saudi Arabia, you get 6 minutes of a total solar eclipse, and people are going to come to this country to witness it. And this is going to be one of the largest tourist events the Saudis ever seen. And it's going to be great, but we need to prepare for it because it's also going to be in the middle of the summer. And can you imagine being in the middle of the summer stuck somewhere in Saudi Arabia? Because it does happen. We saw it happen in the US. The US has a ton of roads. And yet, after both the 2017 and the 2024 eclipses, the traffic was unbearable. This was one of the things that that task force that lasted for 7 years was trying to prevent, was bad traffic. And yet still, this headline from the Chicago Tribune is from 2024, where folks said they had to wait in 15 hours of traffic. Okay? Let's not have that happen in Saudi Arabia, because someone waiting in 15 hours of traffic in August might die, actually. And the traffic that happens during eclipses actually causes more traffic accidents. So this is a really big deal, and there's a lot of different folks we need to get involved. The hospitality industry, emergency services. KAUST needs to have a plan for safety. The kingdom needs to have a plan for safety. And a plan for science. There's a lot of science we just talked about that can be done. These are 6 unique minutes to study the sun, to study the Earth's atmospheric response to the turning off of the sun. You can do solar science, you can do lower atmospheric science, you can do upper atmospheric science. There's a lot of different tools that you need to do that, and I don't know what currently exists in the kingdom. But I, very much as a scientist and as a former KAUSTian, want to make sure that all of this instrumentation gets to the kingdom to take those valuable measurements. Because there's not going to be another total solar eclipse in Saudi Arabia until 2034, and there's not going to be another one over KAUST until 2053, and both of those are going to be half as long as the one that's coming up, which means you have twice as much data to take next year than you will in the next 50 years, and it is extremely valuable. Because of the cost of this instrumentation and the way that it could be efficiently deployed to take the maximum science, I just put here kind of a recommended schema of where I would place all of this instrumentation, mostly along the path of the eclipse, but also some orthogonal to be able to study those larger scale structures for the atmosphere. And I am happy to help enable this. Again, this is incredibly important. I love KAUST, I love the kingdom, I love science. That's why I'm here giving this talk. And there's also opportunities for what we call citizen science. There's a lot more on this website. In the interest of time, I'm going to point you there. But this science is not just stuff that can be done by researchers, but it can be done by the entire community, by the entire kingdom. There are a lot of ways for folks to get involved in science that aren't using rigorous instrumentation, using previous knowledge. So I really encourage the kingdom and KAUST to take advantage of every opportunity to study and experience this eclipse. And I'll leave you with a few takeaways. I've said this is amazing. I can tell you personally it's amazing, but I've never witnessed a 6-minute-long eclipse, so this one's going to be even better. It's coming to the Kingdom and to KAUST on August 2nd, 2027, in the middle of the day, and it is the longest eclipse of this century. There's so much science that can be done, but you need to have the right instrumentation, and you need to start working on that now. And there's also a lot of other things to prepare for, to make sure that anyone who comes or anyone who's already in the kingdom stays safe during this event. Fortunately, I've done this before. Many folks have done this for the past couple of decades, where eclipses are a really big deal. And so there are resources. I am happy to help. I am very excited for this opportunity and for you all. So I'll leave you with a beautiful picture of a total solar eclipse. Thank you.
We have time for questions.
Oh, can I grab my water?
Thank you so much for such an inspiring talk. I would say we have time for a few questions, but to start with, I would like to understand from your past experience, where should we start? You know, because I can see there are so many things to do. So where do we start?
So you need to start with the things that have the longest lead time, and those two things would be, one, Eclipse glasses, because there's a special filter. It takes time to manufacture them. You maybe only get them in batches. And so, today I would start ordering solar eclipse glasses from those safe vendors. And number two is
Let me show you this one.
See, he puts those on. He can't see you.
So
there's no light. He can't see you.
In 1 year and 190 days, you'll be all like this, believe me.
It's a good look. It's a good look.
But I see nothing. Yeah, it's true.
And then the other thing would be acquiring the scientific instrumentation to do the studies, to take the data, because that also will take time to acquire and set up and calibrate and everything.
Okay, thank you. Any questions from the audience? Yep.
Oh, there's one up there.
Do we have a microphone or?
Oh, hi. Yep.
We have microphones here. I have a question, but others move ahead to the microphones. Should I start?
Maybe start, and we'll see.
Okay, don't be shy, folks, right? If you have questions, come up in the aisle and poke Alex a little bit. Alex, lovely to see you again.
Hi, Martin.
Thanks for this really fascinating presentation. As a scientist, I, of course, have a scientific question. Not on technical details, but on following up on Thibault. So you said prepare and get those things that have long lead time. For me, that would be probably the scientific instrumentation. Now, you showed some devices here, but we may not have those, and we may only need them for 6.5 minutes. So is there a system or an organization where we could borrow these instruments so that we say, okay, we work with NASA, we work with ESA, European Space Agency, to bring certain instrumentation in a coordinated fashion for a week to the kingdom to make these measurements for 6 minutes instead of purchasing instrumentation and then it sits around?
So I have two answers to that. One is that the instrumentation to study the upper atmosphere is worth a long-term investment because it also studies space weather, which I, for a fact, know that the National Meteorological Society of Saudi Arabia is interested in pursuing. They've already expressed an interest in purchasing space weather equipment, which is the same equipment that is used to study an eclipse. So that's stuff that you could purchase and use for a long time. For the other equipment that, again, as you say, you may only use for 6 minutes this decade, this is an excellent opportunity for KAUST to partner with other institutions that may have this instrumentation. There's no borrowing program that I know of, but other folks who have this instrumentation want your data and your access to the sites and everything. So, if and when KAUST and or the kingdom acquires this data, you're going to have people knocking at your door to get it, right? You're going to have the Harvards, the MITs, all of the best universities, the Oxfords in the world wanting to partner with you to get that data. And so one of the ways that you can procure the instrumentation is by developing those partnerships ahead of time.
Okay, thank you.
Excuse me?
Yes, please.
I'm up here.
Good.
I have a question. It took a while to get to the microphone. Is it my turn or her turn?
Go ahead.
Yeah, that's great.
I'm sorry, I didn't see her.
It's fine. Go ahead, and then we'll come down.
Yeah. Hello. Great talk. So I have a question regarding the toposphere, I guess. So with the solar eclipse and the increased or decreased radiation and the temperature change, what effect do you think it will have on the growth or mutation of microorganisms? Because we know that different concentrations of UV light cause mutation in certain microorganisms. E. coli sometimes fluoresces, and Staph aureus as well. And these mutations sometimes lead to antibiotic resistance or increased virulence in some organisms. So how can we, is it worth taking that into consideration or investing some time to research this?
That, I personally don't know the scales at which these mutations happen, the time scales. The solar eclipse is only 6 minutes. So, you're turning off the UV radiation for 6 minutes, which if something important is happening during those 6 minutes, or if the timescales are really short, then I guess it would matter. But otherwise, the light comes right back on, and so I think it's probably less relevant to those mutations. But again, I don't know. I'm not sure.
Increasing UV light causes more mutations, and sometimes it can kill the organism. But so decreasing it,
So yeah, it just depends on if those 6 minutes, of non-UV radiation will make a difference.
Okay, thank you.
Yep.
And if I may just add one point, is in the upper atmosphere, heavy particle is also a big factor in DNA mutation. So it's not just UV at that level.
All right.
Yes, please, question.
Thank you. Thank you, Dr. Lockwood, for your talk. I have so many questions, not because your talk was lacking, but because it was extremely interesting. One of my questions are, during totality, what are some constraints that limit coronal measurements, like that cause, for example, noise during your measurements, and how do you overcome those constraints?
That's a good question. Fortunately, most of the constraints are perfectly blocked out. I would say one thing is clouds. You can't control the weather. That's probably the number one thing that could get in the way. Fortunately, it's not usually cloudy here in Saudi in the summer, but you can't control the weather. So any kind of weather is going to completely mess you up in terms of the solar observations. Otherwise, it's just being prepared, being able to measure the right wavelengths, having the right tools to really get, to be able to study the glow and get as many photons as you can.
Would stray light also affect it, or is that during totality, is that not a thing?
It's not a thing during totality. There's no stray light. Yep.
Oh, wait, that is pretty cool. Thank you.
Thank you.
I have a question, if you may. So, when we discussed psychology in the terms of solar eclipse, so one aspect in the Islamic religion is fearing solar or lunar eclipses, right? So usually, we as Muslims, whenever we do witness these phenomena, it's usually immediately to the prayer room. So how does one, as a scientist, how does one cope with this challenge? There's a certain anxiety with it, right? So in your experience, how does one cope with this, unique challenge?
That's an excellent question, and I'm not a Muslim myself, so I didn't want to go into, I didn't want to broach that at all. However, since you asked, first of all, there's definitely the opportunity to set up all of the scientific equipment and leave it, so that anyone who needs to go run to prayer, as you said, or do whatever they need to do, can still do that, and the science can still happen, which again is really important. But the other thing is, one of the things I think is beautiful about the Islamic culture is that it has changed and evolved to grow with the times. And we are in the age of information where, there may be fear, but there are so many resources out there to prepare you and explain that there's no danger at all. And so, I just encourage folks to get that information, prepare themselves, and understand that even though there is a very real, you will get goosebumps, real chill and fear that could happen, to know ahead of time and try to prepare yourself to handle that, suppress it, and be able to experience it if you can. Everyone has their choices of how they're going to handle things, and that is beautiful that we have that choice. But I do think that there's opportunity, especially within, such a dynamic and growing, adapting culture like Islam, to be able to prepare folks to experience it more willingly.
Lovely answer. I'm very thankful, and I very much enjoyed this topic. I usually avoid anything with this topic, but the way you explained it was very lovely, and I thank you for your time.
Thank you. Thank you.
Maybe one here, and after we will finish. Yes, please.
Thank you for inspiring talk. I have a question. The solar eclipse will be a valuable opportunity for the scientific research. So what is the maybe one of the most interesting research you think will be verified or or theory to be proved in this test? I'm sure many people have did some preparation for this solar eclipse.
Yeah, I think for me, again, what I've learned, and I'm not an atmospheric scientist, but the relationship between vertically propagating waves in the lower and upper atmosphere is unknown. People think that something in the lower atmosphere can affect the upper atmosphere, and vice versa. But again, this is a really unique laboratory experiment to turn off, one stimulus, potentially even inducing the waves by turning off that stimulus and then measuring the response. And so even though we've had past eclipses to be able to study this, there just either hasn't been enough data or, it really is just about getting more data. The more data points you have to improve your models, the better. And so I really think it's the relationship between that lower and upper atmosphere that's going to be extremely valuable and help us, discover some stuff.
And if I may add one thing that is not necessarily scientific, but more for the younger generation, it's a unique opportunity for them also to be brought into science. And sometimes this type of event can really trigger something in the youngest, population.
It is an opportunity for inspiration. Huge.
Maybe one question here.
Thank you so much for the great presentation. I just have a question that might sound naive, but from a non-expert. You already were in the 2024 eclipse, and I'm not sure how long was it, but it's a bit shorter than 6 minutes. And I think data was collected. So what value do you think this new data will add, given that you are witnessing the exact same phenomenon?
That's a great question, actually. So two things that come to mind. One is for the solar data, the sun changes on an 11-year cycle. And so, the sun changes on an 11-minute, basis. The sun changes every second, every hour. So what's happening on the sun and being able to study that is going to be completely different from one day to the next. And, a difference of 3 years changes where you are in a cycle a lot. So that's definitely one piece, is that, the solar conditions are completely different. And then for the atmosphere, again, you have global climate models. There's so many different factors that you could take 100 eclipses and you wouldn't have enough data and enough spatial coverage and temporal coverage to actually constrain your models that well. So it's really just more and more and more data.
Thank you. Yeah, thank you.
I'd like to add one point just to finish up. You know, it's exactly, some people, you know, have also compared, you know, a solar eclipse is exactly like when you had 9/11 or even during COVID, the change in the human habits, you know, has effect. And so, from a scientific point of view, you may want to have COVID every year just to be able to see the atmosphere's effect on the atmosphere and things like that. Yeah. So I think the more we have, the better it is also. Yeah. You know.
Gotcha. Thank you. Yeah.
Yes.
Please, and last one maybe, I think.
Thank you for the talk. I really enjoyed it. For those who are strictly interested in the imaging part, the aesthetics, my understanding is that almost every home in Saudi Arabia, every one of 3 homes has a very simple digital camera. What else would you recommend that they use to capture this in the best way possible?
I mean, during the eclipse, you can take a picture of the sun with a digital camera. You can take it with, you know, your iPhone. It's not going to be the best picture, but a digital camera would be better during the total solar eclipse. Before and after, and I mean every second before and every second after, you absolutely need a proper solar filter. I'm not a hardware expert, but I do know that they sell them online very abundantly. So, you know, if you want to document more than just the totality, you need a special filter for your camera. That being said, you have to take it off immediately during totality, otherwise you're not going to see anything. So, that's, yeah.
But frankly, I mean, the hole in a cupboard, you know, or any, you know, a shoebox, frankly, yeah, a shoebox, you remove one part, you make just a hole, you would be amazed already about the size. You know, you would have a small, you know, maybe 5-10 centimeters. Simply the visual effect is already huge. So you don't need big equipment, I would say. After, if you go for the equipment, you have to be careful, because the problem is not during the eclipse, it's before and after, you know. But apart from that, you know, it's very simple, I would say.
Thank you.
Anyway, at that stage, I would like to thank you again, and I invite everybody, if you want to talk with her, just after. So thank you again.
Thank you, Dr. Lockwood, for the fascinating eclipsing keynote, and to Dr. Thibault. Just a few reminders and announcements for some. At 6 p.m. this evening, right here in the Auditorium Building 20, there'll be an improv show open to the whole community. So if some of you already left, you can tell a friend that they can join you. And tomorrow, for anyone registered for the Al Balad trip, the bus leaves at Al Khazama Hotel at 2 p.m. And don't forget to check out and have a lovely weekend from the WEP team. This comes from the WEP team, and we hope to see you on Sunday at 1 p.m. right here for another exciting week of WEP.
Que quien sufre inmola para no estar solo.